So in many cases we define the topology by just specifying what all the open sets are. However, what is much more convenient in practice is to follow a strategy we did for the real numbers. Okay, so for example, for real numbers, we'll say whatever this means. If I look at all intervals, a, b are in R, and a is less than b, so we look at all open intervals, is a basis for the topology. And so along the way, when we proved that this was a basis, we proved 1/2 sort of automatically, or actually maybe even almost 2/3 of what is required to be a topology, which will just carry over. And then we saw a condition, a geometric condition on intervals. So not everything can be a basis, and we'll see an example to see that. And here in general we'll have to understand what that condition is. Okay, so well, we can define things in a clear, fairly obvious way. So we say that B is, so remember open sets were unions of these open intervals. So similarly we say B is a basis sorry, let me write that a bit clearly. B is a basis for omega if, first of all, B is contained in omega, so every element in B is open, and every or it might be cleaner to write omega is set of all unions alpha in A of V alpha of collections such that A is a set, and for all alpha in A, V alpha belongs to B. Remember, we defined this to be omega B, and we proved a couple of properties about omega B, and indeed those will carry through here. Okay, so if omega is union of these, we look at unions of subsets of B. They are exactly the open sets. By the way, this implies this, because every set is a union of a so I put this in brackets, so it's a collection of open sets, but you see every set is a union of a single one, so is a union of itself. And so if I say omega equals this, then it means that of course the basis itself consists of open sets. Okay, so this is the definition of an open set, and so by definition our topology on R was a topology with this basis. Okay, and so we have seen the following rather useful characterization. Okay, we have seen that some set, let us say V, belongs to omega B if and only if for all x in V there exists, let's call it W in B. I had called it J to suggest an interval last time, which is J is sort of like I, but now we won't think of it as an interval. W is an open set. So there exists W in B such that X belongs to W and W is contained in V. Okay, so we see that a point is a set is a union of sets in B if and only if for any point here, and here is V, there is this basic set which is contained in the set V and contains this point. Okay, and so as a conclusion, thus B is a topology is a basis for omega, the specific omega. Well, it's equivalent to, of course, by definition, omega equals omega B. By definition, that is every set in this is, but often easier to verify is the second condition because it does not involve quantifying overall collections. Okay, so for all V in omega, if I tell you that something is an open set, in a topology, I mean, you're given the description of open sets and you're given the collection of sets, described collection of sets which forms a basis. You want to verify if it indeed does give you the correct topology. Then for any open set, we need for if and only if for all x in this open set, there exists W in B such that x is in W and W is contained in V. Just pointing out, we can get away without quantifying our collection. So this is a useful characterization and we have already proved this. Okay, but the other question we want to address, which is a little bit deeper, which we addressed when we got to R, is asking when is B the basis. I'm given a collection B, when is it the basis for some topology? Okay, so here is the question which we can turn to next. So here's the question. So when so suppose we are given B and this is contained in 2 to the x and x is set. When is B a basis for some topology? Okay, so we won't answer this immediately, but first let's note down a couple of simple things. Firstly, okay, so if so, omega is omega B. Okay, so the question is equivalent to the following question. I can reframe it. When is omega B a topology on X, or topological structure on X? Okay, so this is the question which we need to address. Well, there are a couple of conditions. First of all, a simple condition is, firstly, X itself is in omega B if and only if for all x in X there exists V in omega B such that X belongs to V. It is contained in X is redundant. Okay, so this is equivalent to saying that union of all the sets of B in, well, let me call it W for consistency. If I look at all the elements in omega B, in B, there exists not V in omega B, that was no condition at all. By our earlier criterion, there is a basic set such that X is in V and V is contained in X. Okay, and that is just asking whether if I look at all W in B and take their union, it's X. Okay, so first of all we need to assume that the union of all sets in this is this. Okay, so henceforth assume this. Okay, this is the boring condition in a sense. It's just telling you that the topology is everywhere, the basis is everywhere. So if there are some points that are not even contained in any basic set, then the whole space won't be open. So we get a contradiction. But is that all? That's a silly example. No, because we can look at a slightly more interesting example. So B is, let's look at the subsets of natural numbers. Let's take A contained in N such that A is infinite. We are reusing the same example we saw earlier. Okay, so now what is omega B? Well, it's the union of empty infinite sets. That could be the empty union, or it could be A contained in N, A is infinite. Okay, so perhaps it's not ideal to use the same notation A, though it's mathematically absolutely correct. So what we have used here by passing to this is that if I take a union of infinite sets of natural numbers, then this is either an empty union, in which case it's the empty set, or it's a non-empty union, in which case the result is infinite. And conversely, of course, any infinite set is a union of infinite sets. It is a union of a single infinite set, if you like. Or at the other extreme, you could take, well, you can't take union of its points, which are not infinite sets. But there are other ways also in which you could express it as a union of infinite sets. But anyway, this is clear, and we saw this is not a topology. Okay, so namely, as there exists V1 and V2, for example, prime numbers and even numbers in omega B, such that V1 intersection V2 is not in omega B. So just a random collection will not form a basis for a topology. Okay. So in linear algebra also you need an independence. Here it's a little more subtle. These bases are not as powerful as bases in linear algebra, but conditions are also more complicated. They're less canonical, they're less useful, but still they're pretty useful. But you see, you can't just take an arbitrary collection and see this. You need a condition on intersection. Now if you think back about how we dealt with real numbers, the property 3, which we have dealt with right now, it needed an extra condition. Okay, and by the way, we do know phi. Firstly, we have this, and then also phi belongs to omega B always, because it's the empty union. Okay, so phi belongs to empty. There is a condition for x to belong to omega B, which was satisfied by construction in the case of real numbers. And while not trivial, the closure under union was completely automatic. It was completely formal. I will briefly recall it, but it's exactly the same proof goes through for real numbers. But closure under intersections used some geometry, and so not surprisingly, it's not always true. Okay, so we will characterize it in some sense and try to make it a little bit useful. So with our example in mind, let's get one out of the way, which I said is always formal. Okay, so the property 1 says if, so it says that union, if I take a union of V alpha, this belongs to omega B if V alpha is in omega B for all alpha in A. Okay, so this is the property we proved. And we have our characterization which made this convenient. Okay, namely, so suppose V alpha belongs to omega B for all alpha in A, and we have to show a property for a union. Suppose we take x belongs to union of alpha in A of V alpha. What we have to show is there is a basis set sitting in between. Okay, then there exists alpha naught in A such that x belongs to V alpha naught, and this implies that there exists W in A, so not just in A, but actually not in the index set at all, but in B, the basis such that x belongs to W, and W is contained in V alpha naught, which is contained in union of alpha in A of V alpha naught as required. So this is the same proof. We did it again briefly so that for review. So a completely formal point, but it's very clean given the characterization. So I have a union of a bunch of sets and I have a point in it, and I want to find a basic set. It's in one of them, so you can find a basic set in one of them, and then that basic set is of course in the union. So 1 is always true, 3 is true given the very mild condition that the union is everything. What about 2? We have seen 2 is sometimes false. Okay, so 2 is that, so we need V1 Vn belonging to omega B implies V1 intersection Vn belongs to omega B. So now here is the bit of an issue. Okay, we don't want to really be checking conditions for all of omega b. For example, as far as real numbers is concerned, we didn't want to be checking things for all unions of intervals. But there we managed to just reduce the problem to considering just intervals. Okay, so that's what we will do here. So condition 2. So I'm not going to prove 2. We are trying to understand what is the condition where it is true. So in particular, if we specialize, need the following condition, that if I took v1, vn, or maybe for clarity of notation I call them w's. So if we took basic sets w1, w2, they are open, then w1 intersection wn belongs to omega b. Okay, so you can write it this way. So intersection, okay, so that is, we can think of it two ways, either straight out from the definition, the w1 intersection wn is the union of alpha in a w alpha for some a, and then w alpha in b for all alpha in a. Okay, so given the set A and given W alpha, this is the union. So every intersection is a union of sets on the basis, or it's an omega basis. Or equivalently, often more convenient to verify, equivalently, well, we know a characterization of omega b. Okay, so equivalently, for all x in W1 intersection Wn, okay, there exists W naught, let's say, or maybe better still, we'll call it Wx. There exists Wx in B, such that x is in Wx and Wx is contained in the intersection of these. This is what we actually verified with the intervals. We took a bunch of intervals and then we took the min and the max and then found a smaller interval, and that was contained in all of them. And we found that that was enough, and that is really going to be the content of the useful characterization. We don't have to verify the intersection is closed for all open sets. It is enough to verify the intersection is closed, and intersection is, so finite open sets are closed under finite intersection for arbitrary open sets. It is too much to ask that intersection of basis sets is a basis. Okay, it's true for intervals, but that's a bit of good luck. It's not true in almost any examples. What is happens always but is sufficient is that the intersection of open sets is a union of open sets W alpha. Okay, so intersection of basic open sets is a union of basic open sets, and this can be verified point-wise, as we see. Okay, so that is really what the theorem we have to prove here. So the theorem here is, suppose B contained in X, not X of course, it's the power set, contained in 2 to the x is a collection of sets such that we have union of all W in B of W. The union of all the sets is X itself. This is the condition which says it's not degenerate. And then for all W1, Wn in B, let's spell this out clearly as we are stating it as a theorem. There exists a collection, let me call it W alpha, or why not, alpha in A of sets W alpha in B such that W1 union Wn is, not the union, of course, the intersection is the union of alpha in A. of W alpha, then B is the basis of some topology on X. And as emphasized, this can be rewritten equivalently. Given any point here, X here, there is a set, basic set, which is contains the point and is contained in this intersection. Okay, so remark equivalent to equivalently, given all the other quantification for all X in W1 intersection Wn, there exists Wx in B such that X belongs to Wx and Wx is contained in the intersection of these. This is the easier to verify condition because it involves less quantification. Okay, and the other remark here is saying that B generates a topology is this is equivalent to omega X is, or not omega X, omega B topology. Yeah, so omega B is a topology. This is equivalent, and let's make it remarks. And the other thing is the converse is also true, that we essentially saw. If the first condition is violated, then X is not open, and if the second condition is violated, then we have sets, namely these basic sets itself, whose intersection is not open. So the conditions on the topology. Okay. So let's recall the proof. We have done things. Okay. So A implies the condition 3 for a topology. So at least locally, I'll assume that you know the numberings. We have used them a lot. And 2 is always true. That's what we just saw. Okay. Remains to show B implies 1. That is, can replace. So in B we had Wi in B by Vi in the omega B. So if we know that intersections are nice for sets in B, then they are also nice for sets in omega B. Okay, we'll write this as a lemma, and thanks to our criterion, I'll restate it in the following way. If V1 Vn belong to omega B, they are open sets in the topology generated by B, or the candidate topology generated by B, unions of sets in B, and X belongs to V1 intersection Vn, then there exists, well, all I had to show is there exists an open set, but in fact there exists a basic open set in W such that X belongs to B and B is contained in W. Okay, so this proves the result clearly because W belongs to B and B is contained in omega B. So we have any X is contained in W, which is, not X belongs to B. Any X is contained in W, and I'm afraid that was a lot of nonsense there, and W is contained in V1 intersection Vn. So X is in W and W is in V1 intersection Vn. So V1 intersection Vn is the union of the sets Wx, let's call this, these over X. Okay, so recall here the point that I have made, hence V1 intersection Vn is union of X in the whole set V1 Vn of Wx, and this is in omega X. So it follows from this result, And so let's take a proof of this. Of course, this follows exactly the pattern of real numbers, except that in the real numbers we did some work, and here we have hypothesized it. Okay, namely, so as x belongs to v1, vn, x belongs to vi for all I, which implies that there exists wi in B such that x belongs to wi and wi is contained in vi. Okay, so this implies that w1 intersection wn is contained in, so x is in this, which is contained in v1 intersection vn. Okay, and now by hypothesis, there exists wx in w1 intersection wn such that x is in wx, wx contained in this such that x is in wx and wx is basic, but this is contained in v1 intersection vn as required. And let me emphasize, this proves the theorem. Okay. So to summarize, there was only one non-trivial condition. So that's one thing we saw. We saw that there was a non-degeneracy condition, which is essentially simple. That is the condition that the only that every point is in some basis element. And putting that aside, the unions were automatic. And that is, arbitrary unions are closed, so it's because union of union is union essentially. So that arbitrary union, that the topology generated by a candidate basis is closed under union was automatic, but closed under intersection was not always true. However, we don't have to verify it for all open sets. It's enough to verify intersections of basic open sets are open, and we can further simplify this by using a pointwise criterion rather than for generating a union in this case. This will be very useful in defining all sorts of topologies. We will see one step further beyond this, where we will use what is called a sub-basis at times for a topology.